Good morning, everybody. And Nicholas, thank you very much for organizing and having us all to your beautiful country once again. It's the third time I've made it to this meeting over the last 8 or 9 years. So, and always a great pleasure. We got here a few days early this year, so I've made my ritual donation of blood to the local sandfly population. So in case they needed additional Italian stock or something. So but yes, so I'm ahead of time, so maybe you won't hit me with those things so quickly, but this is a relatively short talk. So there's some assertions I want to make about the sort of dynamic between AI and HPC, and I have a lot of evidence to support them, but because it's supposed to be a 20-minute talk, I've deleted most of the evidence and just stuck with my obnoxious assertions. So you will get to hear all about them. So yes, I'm Dan Stanzione. I'm here from the Texas Advanced Computing Center, which is at the University of Texas at Austin. A couple of my colleagues will be speaking later in the week, Omar Gattas and Karen Wilcox, also from UT. But we're on the sort of supercomputer side of the house, and normally I would tell you some about the center, but again, given the length of the talk, I don't really want to talk about TAC or our plans so much. It's just sort of the big trends I see going on in the sort of AI and HPC and where we need to go from here. Beyond just this one observation, which informs some later things, but even though AI has sort of sucked most of the oxygen out of the room on HPC topics, HPC in its sort of raw primitive form still remains incredibly important across science and engineering and almost universal. And I was struck sitting at a user meeting we had a few months ago for users of one of our big machines and just listening to all the talks at the sort of range of scales, just in the talks that I heard in sort of half a day of sessions. And if you think about the scales people were working at, I heard about things where the time step was picoseconds and the time step was giga-years. So that's a 10 to the 28th spread in the size of the time scales. There's 30 octillion picoseconds in a giga-year. Had to look that up. I went to some very unpopular parts of Wikipedia to find this stuff. So the length scales were measured from angstroms to megaparsecs, which is a 10 to the 32 spread between the smallest length scale and the largest length scale. And there's 300 nonillion angstroms per megaparsec, if you were wondering. I stay awake thinking about these things. So, but it's hard to find any problem left in the universe that you can't fit somewhere between those boundaries with a 10 to the 32nd scale. It's also hard to figure out that stuff if you use 6 bits of precision doing AI. And you have to multiply numbers with that sort of range, dynamic range between them. So I think the premise we all start with, or we wouldn't be here, is that HPC is incredibly important for all fields of science across an incredible range of scales. But now we have the AI piece in what we do, and advanced computing really at this point includes AI. It's not one or the other. My talk is about, is one going to destroy the other, which still remains possible. But but what's happened clearly, at least in the marketplace, is we had this sort of healthy $10, $20 billion business going in HPC, and then AI came along and not only captured the public imagination, but it captured most of the computing marketplace, right? There's overly optimistic estimates that put the economic value of AI at $9 trillion by 2030. Maybe half of all jobs in the world being impacted by it. But if you look at the hardware and infrastructure market, building data centers, buying servers from them, I think Andrew buys most of them at this point. There's about a $300 billion a year market. And I read recently just the big 5 companies, the cloud providers, are spending $300 billion this year on AI. There's not necessarily that much revenue. If you look at, say, Microsoft's cash balance, for instance, it's gone down about $60 billion over the last 3 years as they built out this AI infrastructure and made this investment. But I think among the important lessons for us is that at scale, the technologies for AI and our traditional high-end scientific computing are almost indistinguishable, although the couple of distinguishes left still matter. But in one sense, it's driving a lot more investment into our sort of HPC technologies that we need. But we're going to have to adapt to that, and that's going to be sort of my main method. So if you sort of look at the disruption, and there's a lot of again, a lot of hype around what AI is going to do. I think there is a pretty strong debate to be had about how much of our sort of traditional simulation workload will actually be impacted by AI. And I think you'll hear from some of the other speakers this week about that, something I talk to folks about a fair amount. So, but I think it's fair to say that AI might replace some of our simulation workload, but it's clearly debatable how much will happen, and it's clear, to me at least, that it will not be all of it, right? We're not going to just replace simulation with AI whole hog. It just simply won't happen that way. Despite that, it'll probably still have a pretty significant impact in the overall science workflow, right? I mean, your ability to data mine from papers, for instance, might be much different because of AI, even if you're not replacing your core simulation for it. So I think, the degree of disruption we're going to see in the sciences is something that we can debate during the course of the week. But one thing that's not up for the debate is that it has disrupted our marketplace for scientific computing, and the business of scientific computing has become substantially different. And just a couple of recent things beyond that, 300 billion being bigger than 10 billion, and even vendors can do that math. And missing on that math explains, say, I don't know, Intel right now and their near-death experience they're going through. So but this is a recent Hyperion analysis, but sort of estimating the server market. And so if you go back to 2019 there, that first sort of pinkish line, I should never be in front of an audience trying to describe colors, but was the estimate in 2019 of what the sort of worldwide HPC server market would look like. Sort of, 3% a year growth. Maybe it would get from 15 billion to 20 billion over 9-10 years there. The black line is sort of the new forecast, with the shaded regions being what's actually happened so far. And you see that estimate has gone from like 15-ish billion to 40-ish billion just on the server sales side of things. This is from same Hyperion paper on estimated cloud spend and how that has changed, just going back to 2022, and you see it exploding over the last few years. And this is both on-prem and cloud spend for end users on this, growing to 80, 90 billion a year in the next couple of years. This has had some interesting side effects if you buy computers like we do. So the cost per bit of flash storage in particular, but for solid state storage, if you measure in 2024 from like February to October, the cost per bit went up about 60%. The last time the cost per bit of storage went up was never. It's been pretty much going down 30% a year since 1950 until last year, right? When we could make a circuit to store a bit, until this past year was the first time the cost of storage went up. I've also noticed, because one of the reports we write for the people who fund us at TAC is sort of what's the cloud equivalent value of the cycles that we deliver. We just measure the CPU time and GPU time we deliver. And I noticed last year I didn't deploy a lot of machines, but the number went way up. And the reason is end user pricing in the cloud for both CPU and GPU time. Then if you just look at, I pulled Amazon rates for this, but if you compare them to the year before, for the same chips, not for newer chips, not for more cores, but sort of the per core price has gone up a little over 50% in the past year, right? So the same computing you did a year ago costs 50% more now, which again is something that has never happened since we counted computers, did computation by sliding beads on strings, right? The price has gone down every single year. And I'm not sure we're ready for a world where doing the same computation costs more with each passing year, especially with people spending literally billions to train single AI models at this point. So, so the disruption in AI, again, the science impact is debatable, but the market impact is sort of indisputable, that it's changed the world in the way that we buy computers at this point. But at the same time, all of this modern AI infrastructure, I would argue, exists primarily due to the work of the high-performance computing community, many of us in this room, over the last 50 years. And so, I took a class in neural networks in the late 1980s, where basically the same techniques were there. The sort of fundamental roots of most of the algorithms that they use in deep learning now easily go back to the 1960s, and were theorized in some cases in the 1950s. But they took off now mostly because we needed to have computers fast enough to do it. And some of that advance that everybody credits it to is the physics, the silicon process getting better, but you see almost an equal advance from things like architecture improvements. We weren't going to run AI on GPUs in the 80s because there weren't any. and algorithms have played an almost equal role, right? With the BLAS, FFT, our linear algebra methods are a lot better than they were in the 1960s in terms of their efficiency to run on these sort of deep vectorized pipeline circuits that we have now. And in fact, the thing that sort of exploded AI into public consciousness, through the large language model, ChatGPT, that kind of stuff, brought it to the public. But just a couple of years before that was an algorithm change that enabled them to get to that scale, which was the Transformers paper, which you've probably all heard of out of Google, in 2018. It's called Attention is All You Need, which said if you did the attention step in the neural net, you could ignore most of the other steps, which broke a lot of the data dependencies and went from how many can we run on GPUs in one box to let's run on 5,000 GPUs across a data center, was enabled by that algorithm change that really did it. So it's been part physics, part architecture, part algorithms that have got us to this. And a huge amount of the modern AI looks like HPC. In fact, I was reading a paper recently and they said, we just need 3 keys to build large language models: high performance IO, high performance computing, and high performance communication. And I'm like, yes, that's exactly what we've been doing for the last 50 years in the HPC community. And if you look at how they break them up and scale them, it's data parallelism, operator parallelism, pipeline parallelism, the exact same techniques we use in scientific computing. So AI in its current form wouldn't have happened without the HPC innovations, many of which were open source and didn't cost billions of dollars, which is another part of the lesson here, is that so AI needs fast interconnects. And this is where I get great schadenfreude with the cloud vendors, and that for years they told us, why are you spending all this money on fast interconnects? We don't need to do that. You should just eschew them and run in the cloud. And then they completely pivoted around 2019 and have become the largest consumers on the planet of fast interconnects. So InfiniBand was originally designed as a storage network, but really exists because of the HPC market that adopted it, the fast, low latency interconnect we use in a lot of big clusters. Again, the cloud believed in 2017 or so that was a ridiculous thing to do. Why ever do it? In 2023, Microsoft deployed 40,000 kilometers of it. I have about 300 kilometers in my center, so that's a lot. It was more than was made in the world before 2023 in a year of InfiniBand. Maybe when we hear from Andrew later, there's an update for this year, but they've been deploying it about as fast as humanly possible and faster than they can make it. AI requires message passing, right? When you break these things up, you hand them back and forth, right? The message passing interface was an open source standard built in the HPC community in the early to mid 1990s, still ongoing. DK Panda might be here. I didn't see him come in yet. But yeah, hey DK, who builds the most popular implementation of MPI was here, but it's been an open source thing. It's made it around the world, and it's under the covers in all the big libraries. AI needs heterogeneity, something that again was, nobody was building into desktop computers, but was built out in the HPC world, right? The most popular hardware building block is the GPU. The whole notion of doing general purpose computing with GPUs, the general purpose, special purpose processors, I'm still not over that, started back in around 2004 when Ian Buck wrote CUDA and things like that. But that was to do high performance computing originally, and now it's the standard building block of AI. They need fast, large-scale file systems. They need liquid cooling. If you talk to cloud vendors, when we were designing, we're adding 15 megawatts of data center now. When I started talking to all the data center vendors about building that, we're like, we'll be doing air cooling forever. And that was in 2018. And now they're like, air cooling is ridiculous. 5 years later, we're going to do liquid cooling in every rack because we've hit 220 kilowatts a rack. And counting. So all of these things that are necessary for modern AI came out of the HPC world, which is now going to kill. So if you need good HPC hardware, that means, with an exception or two, AI is going to drive companies to invest in that. If you need good HPC people, you're probably screwed because those same companies are hiring all our people away at exorbitant salaries at a ridiculous rate. And this is just some data backing this up. This was some information from Meta, Facebook, about how much time their AI algorithms spend with the GPUs idle because they're waiting on the network, right? As they slowly figured out network latency and bandwidth mattered, right? And so if you spent recently, what's the estimate for Stargate? $500 billion on GPU infrastructure, and then you tell people that 57% of your time is spent waiting on I/O, that's $300 billion worth of your spend that is not working because your I/O is too slow. So, but I would say the thing that's probably most overlooked, and I've been yelling about this, but then in the last few weeks, China came to my rescue on this. But is that as you grow scale, and this is a long-term lesson in HPC, sort of every order of magnitude, you need to go back and pay real attention to your algorithms and your implementation and your code efficiency. And if you don't, you run incredibly inefficiently. And I've been saying that most of AI is computing zeros that we already know are zero for a long time. But then DeepSeek came out a few weeks ago from China and pointed out that you can do it a lot better. And there's another slide or two on that in a minute. But based on a quick analysis, best practices, nothing really revolutionary. It's paying attention to performance that made this happen. So unfortunately, I think the problem we're facing is that we're losing sort of the connection between the big AI world and the fundamental research community, the academic research community, smaller labs, smaller countries. This is a breakdown back to 2005 of where the papers about notable AI systems by some magazine's definition of notable AI systems, might be The Economist, I can't remember, Our World in Data here. So 2005, it was 100% academic. I've seen another one. If you go back to the 60s, it was pretty much 100% academic. And then the green line coming in is industry, right? And how much of the published papers and notable teams are requiring these multi-billion-dollar infrastructures, or at least think they require multi-billion-dollar infrastructures to make innovations, and how much that's sort of made academia a tiny part of it, and industry the huge part of where that happens. And there are some issues with AI. One is, of course, what it's done to hardware costs. So that could just bankrupt the planet, but details. That's not the only problem. Again, if we're going to work between angstroms and parsecs, I need precision to do that, right? An awful lot of precision in HPC. But to figure out if connections in a deep neural net are sort of on or off, or strong or weak, you don't need a lot of precision, right? So historically, we do scientific computing exclusively at 64 bits. AI was at 32, then 16, then 8, now 6. There's some 4. I've seen a single bit estimate of this. We're not going to do science at 6 bits. But the downside is none of the vendors, the major chip vendors, are making fast 64-bit circuits for science. If you look at sort of double precision performance roadmaps, they're basically flat, for the next 4 or 5 years from chips. So our traditional, in a couple of years, it's going to double, is not going to happen when we look at the sort of precision we need for scientific computing. And then, so that I think is probably the biggest problem. Other large one, if you're worried about the end of the world, is the race for AI has caused us to get rid of all thoughts of cost and efficiency. Again, until DeepSeek came out a few weeks ago, where it was, can we build the biggest data center to train the biggest model before our competition does at any cost? And talking to some of the vendors who laughed behind the scenes about this when I was negotiating a software deal where I was paying roughly 0.33% of what their largest customers were paying in the AI space, is their only question is not how much it costs, it's can I have it now, which is in sort of storage and file systems. And if I can have it now, I don't care what it costs, I'll just write a check and we'll do it faster. And that's been bad for sort of efficiency and power, right? So, Microsoft is restarting the infamous 3 Mile Island nuclear plant on the assumption that nobody has any memory, because that one's had no bad press ever, except for the meltdown in the 70s. So to support an AI data center, I think Google, Amazon, OpenAI are all making investments in small modular or other kinds of nuclear power around this. The current construction of AI data centers for 2025 is estimated to add 75 gigawatts to the grid in the short term. If you run 75 gigawatts for a year, because the thing about AI data centers, if you're training, is they're always on and they're sort of always at that power level. That's 657 terawatt hours per year. Last year, New Zealand used about 40 terawatt hours. So the amount we're adding to data centers per year right now for AI is the equivalent of adding 17 New Zealands to the world's power grid every year. So eventually that might be an issue. So we're going to have to address these issues. And this slide seems out of order, but I'll come back to this one. So how are we going to get AI and HPC to coexist moving forward, given this tension around both power and precision that we're going to need, and the fact that AI is just so much bigger? And I think we need 2 big R&D pushes. So before Nicholas says I'm out of time, the 2 main themes I want to talk about is, one, we need a push in AI efficiency to save the world either from climate change or bankruptcy or take your pick, but to save the world, maybe not from the AIs taking over, but living in the US, can the AIs be worse at governance? Let's take a shot. So maybe many shots before the day's over, Nichols. But so AI efficiency is one push, and the other one is AI hardware for science, which is the fact that we need to live with the fact that AI hardware is going to be what gets built, and how are we going to use this to effectively do scientific computing moving forward. So there's plenty of reason, I think, to believe that both of these things can potentially work. So let's take those in order. Efficiency. So historically, you hear a lot about computing efficiency. It's been about the data center. Can we schedule better to get rid of hotspots? Can we use better cooling technology, right? Can we put the data centers where the power is cheaper? I think to get serious improvements in efficiency, we need to get past this roadblock around data center efficiency, where everything we're doing now is about saving 2 or 3% in greater efficiency, and look at where the big returns are going to be, which is the software side of doing this. So we're going to need better hardware and better software to make real improvements in efficiency. A lot of that will be better algorithms, which you don't need a $10 billion piece of hardware to figure out. But we're simply going to have to do this. I took all these slides out, but for a long time, the myth of data center cooling is that we were doing it to be more efficient. In fact, we were doing it to not melt stuff, right? The reason we have dense liquid cooling, which we've been doing in our data center since 2015 and before, is not the fact that it's more efficient, although it happened to be. So that's the story you tell. It's because to get low latency in the network, you need shorter cables. To get shorter cables, you have denser racks. To get denser racks, again, for the Blackwell generation, we're looking at 225 kilowatts per GPU rack right now for things we're going to deploy this year. This is not a long future thing. And air cooling is going to tap out at 30 to 40 kilowatts a rack. So we're really not doing it for efficiency. We're just doing it to make things possible. But let's think about the software side. So we know that, per peak flop that's available, we get sort of a 5 to 6x multiple moving to GPUs. But we still see that outside of AI, we have a lot of codes that still don't run on GPUs. But the ability to get 5x is a lot more than getting 15% out of making better data centers. We also know, but we don't really talk about in public very much, what fraction of peak that our real software actually gets on most of these machines. And it's single digits a lot of the time. It can be, how far to the right of the decimal point do I have to go to find it? Below 1% in many situations, but software is hard, it's diverse, it's expensive to fix, and it's easy to say I'm going to buy more GPUs. So, but nonetheless, even if we do a mediocre job on making our software better, where I believe we have 2 orders of magnitude to get better, 1,000% potential, it's better than making my data center 10% more efficient with new cooling techniques or things like this. There's just so much more there. And we know it's possible, right? The reason that the 2 biggest machines in the world right now are built around AMD GPUs can be summarized sort of in one chart. It's a little bit old, but but it still holds as you go through generations, right? But in the CPUs from Intel and AMD, we're getting more or less 10 gigaflops per watt. In NVIDIA GPUs, we're getting about 50 gigaflops per watt. The AMD ones, we're getting 85 gigaflops per watt. When you're buying 20, 30, 40 megawatts of power to run your single supercomputer, this is a big driver as to why El Capitan and Frontier in the US, the 1 and 2 machines right now, are built around the AMD technology, is 85 gigaflops per watt, and that flops per byte also helps. But they're more efficient for a number of reasons, some of which have to do with the circuit design, right? Some of which is taking complexity out of the architecture and pushing it back to the programmer. There's no complex branch prediction in a GPU to figure out where your code might go. It just assumes you get that right. So there's not as much branch prediction hardware. There's not as much fetch decode execute hardware. They push memory through an array because moving data across the chip takes more power than the floating point operations to approve it if you have to move more than 2 millimeters. So there's lots of upside, but you have to pay the price in software of doing a harder coding job to get this to work. So But again, this has been shown that it works in the AI space, right? Before we build all these nuclear plants for AI, the lesson of DeepSeek, right? They released something where they actually paid attention to the software and algorithms, and it knocked $589 billion off the value of NVIDIA stock in a single day when it was released, most of which has been recovered at this point, because they realize we're still going to buy more no matter what, because we don't really learn this stuff. But if you look sort of into what's going on there, it's using a mixture of experts, right? Decomposing the big model into several smaller models that's more efficient. If only we'd thought of that in cluster computing 35 years ago. The way they quantize the data, good usage of the GPUs to keep all the various functional elements busy, clever coordination of offloading to the CPUs to make sure you're using the right device at the right time. Really good data curation had a lot to do with it. And a little bit on model designs, but most of the efficiency, again, is just things that we already know how to do, but actually paying attention to how it executes on the hardware. This works in scientific computing as well. Your algorithms have a huge impact. This is just sort of using a lower rank algorithm and to take advantage of the sparsity in data. And again, neural nets are computing mostly zeros and a few ones. It's a very sparse algorithm, but this is some older work, but it's from David Key's team in Saudi Arabia, but doing a Cholesky factorization, traditional scientific computing problem where we get sort of an order of magnitude improvement just by using a lower rank algorithm and messing around a little bit with the precision. So we're going to have lower precision circuits. We can take some advantage of that. There are software ways to do higher precision operations with combinations of lower precision registers. It's not particularly efficient, but given that right now 16-bit precision is 30 times faster than double precision on most GPUs, it may be worth paying a 3x, 4x software penalty. You'd still improve in sort of price per dollar. There are plenty of other both software and hardware things. If you look at improving memory bandwidth on CPUs with both ARMs now, with LPDDR from NVIDIA, which is what we're investing in at TAC, with the HBM chips from Intel, we get sort of a 70% improvement on chips that have the same power per socket and the same clock rate and the same peak flops. But codes run better because we can keep them full. So there's many things we can do at the same power per socket to make things better. Some of them are hard, right? Figuring out how to take advantage of sparsity, figuring out how to do reduced rank algorithms, figuring out how to do mixed precision algorithms using higher order methods. But you can just pick the right number of cores for efficiency and make your code a lot better, right? This is a graph from a paper on a GAN4, which is a fairly well-known particle physics code, but the paper was called Green Algorithms, Quantifying the Carbon Footprint. And so the top curve there is your standard sort of speed up curve where, this code gets really linear or better speed up to about 16 cores, and then it sort of flattens out. You get diminishing returns of adding more parallelism than likely the size of the problem supports, but it still gets faster, so everybody just keeps running on more cores because they're there. The other graph is the carbon footprint of doing that as you get less efficient, right? And so anybody can figure out where the bottom of that curve is and run on the right number of cores and dramatically reduce power, and you don't need $1 billion of hardware to figure that out, right? So we're going to have to adapt to the marketplace here, whether it's for making AI more efficient or to do our AI hardware for science initiative. But this isn't a new thing for the supercomputing market. I promise last slide or so. So we've done this before, right? You just have to remember more than 3 weeks back, which is a lot of memory for, say, the stock market, but or the current government. In 1991, when the Cold War was ended, up until that point, we had the big craze, the SGIs, thinking machines, Convex, and a lot of other companies that no longer make computers, except Cray, which is now part of HP. But the big supercomputing companies that were doing gallium arsenide circuits and custom silicon were all falling apart because the Cold War dividend was going away, where the government, and particularly the intelligence community, say, you build a computer, maybe it works, maybe it doesn't, but we'll give you $200 million for the first one because we want to make sure we stay ahead. And maybe the second one or the third one, and hopefully by the fourth one it'll work. But when that subsidy went away, you had to start competing in the commodity markets, and it turns out x86 volume was through the roof, commodity microprocessors, and it was, let's build clusters out of those. And there was a lot of skepticism that we could adapt algorithms to that. But Thomas Sterling, who's now also at TAC, And Don Becker, who's sort of out doing venture stuff now, but started the Beowulf project a little over now 32 years ago at NASA. Thomas's words at the time were, those of us doing scientific computing needed to be bottom-feeding scum suckers. I was a first-year grad student when he started this in 93, and I built my whole career around this bottom-feeding scum sucker notion for how to do computing. But the gist of this was, silicon's expensive. We can't build custom stuff for our needs. We have to use commodity parts. At the time, that meant microprocessors. Now it means all the chips we're building for AI. Things that fell out of that. The first step in that was Don wrote the network drivers for this thing that was sort of being talked about in textbooks and played around with called Linux. First time it ever talked on a network via Ethernet. You could do a modem connection before that. But adding Ethernet to Linux has sort of worked out, given that it runs the global cloud, most of the internet, 90-some% of the servers in the world, your phones and everything else, right? Networking in Linux turned out to be a sort of multi-trillion-dollar impact thing that Don wrote on a government salary in a couple months. So then figure out the algorithms to use commodity processors. Since then, pretty much the whole top 500 has gone this way, although it was kicking and screaming for a couple of decades to do this. And then the addition of GPUs was writing commodity markets. And this is a place where universities led the way, agencies followed, somewhat kicking and screaming, but we can do this again. And when you look at all the commonalities between AI and HPC, we have a lot to offer in improving their efficiency as they spend $300 billion a year building out this infrastructure. So let's do that. Nicholas is standing up, so I'm going to stop talking. So thank you very much.